we were asked to research ways to speed up a large database for one of our government customers. So we had spent over $1 million on a large SAN. Just quick show of hands, everybody know what a SAN is? I got a couple questions today. Okay, half of you. So when you think of SAN, think of big rack full of hard drives. Hard drives typically run at about 10 watts a piece, so it consumes a fair amount of power and needs a lot of cooling. So we had spent over $1 million on the SAN, and the idea is that the more disks you have, the more performance you have, more capacity, and so on. So during that time, we'd spent a lot of engineering, getting spindles, networking between the SAN and to the servers. We got some experts to do some SQL tuning, things of this nature. And our queries are running at about 16 minutes. And for this government agency, that particular query just it had a shelf life, and it wasn't acceptable to have these things running at 16 minutes. So we were tasked with finding another solution. And this was probably early 2008 timeframe, and I stumbled across Fusion.io. So basically, instead of using a SAN, we purchased 5 of these. This is our native PCIe NAND device called an I/O drive. And basically what we did was we popped 5 of these in the PCIe slots of a server, and we copied our data set from the SAN over to the Fusion I/O drive. And this was like in a morning while I'm drinking my coffee. This wasn't a long drawn out engineering process like it was getting a SAN, engineering it, and getting it working. In the morning, while drinking my coffee, we went from 16-minute queries down to 22-second queries. And when you consider the infrastructure change of this, it's pretty significant. Because before, where I needed over 100 spindles to get performance, now I have a couple of these solid-state devices that are using roughly 5 to 7 watts on average to deliver far more performance. And they're inside the server. So basically, if you're measuring your computer data center by how much your power supplies consume, these are essentially power neutral because they're basically powered by the server that they're in. So we went from basically a server which was about 4U and a couple racks of disks which were 42U a piece down to just the 4U server and the power that it consumes. So a wild dramatic savings in terms of power and cooling. And I'll go into the technology and we'll have some more detail about other customer case studies. So how is this possible? How do we get this dramatic improvement in performance and energy savings? So I would assume most people here are familiar with Moore's Law, but basically Moore's Law states that every 18 to 24 months you're going to have a doubling in terms of performance or density in the modern CPU. So that applies to hard drive capacity in that we can typically get more bits on a platter over time, and thus the bits flying by the head increase in terms of density, so you really get a little bit of a performance gain. But in terms of hard drive performance, it stays relatively flat. And I've been working for this company for 3 years, and it's amazing how little is really understood about this and how few people really understand how bad it's gotten. So to kind of illustrate this point, I went out and researched one of the faster hard drives out there. And if you look at a single hard drive, you're lucky to get about 160 megabytes a second out of a hard drive. In terms of IOPS, which is input-output operations per second, you get about 400 IOPS. And the real killer is the latency. That's 5 milliseconds in terms of when I do a read or a write, I'm going to wait that long before the data actually gets to the CPU. Well, the modern CPU can do tens of thousands of instructions in that time. Now, if you look at the modern processor, this is what's coming out from our major server manufacturers today. These started shipping within the last several months. They're capable of 8 gigatransfers a second, or basically 64 gigabytes a second per socket. And most servers are equipped with more than one processor. So that's a huge disparity between what you can get out of a disk drive and what the CPU is capable of processing. So the way that we typically compensate for this is we build these large disk arrays with spindles to try to scale out the number of disks to share the load from the CPUs. I was working with Lawrence Livermore National Labs, and I'll go into the case study a little bit here in a couple minutes. But basically, we had a single 1U pizza box that could drive 1 million IOs a second. If you have 5 racks of disk, and you're getting over 300,000 IOs a second, you're doing pretty good. So it is a wild disparity that you would need that many disks to fully feed just a couple CPUs in a 1U pizza box, which is typically the most anemic server in your data center. So this is a great chart that I borrowed from a Microsoft presentation. Mark Agar put it out, and I believe it was referenced in one of the earlier presentations. But basically, there's a great paper that goes into green IT and IT energy productivity. But if you look at this, it's showing basically improving power supply effectiveness and power utilization versus CPU utilization or server utilization. What a large difference it is to actually fully utilize your servers or your CPUs. Now, this paper was more focused around things like consolidation, but this absolutely applies to making your CPUs more active in terms of getting more data to them. So with traditional storage, you can't feed enough data to your CPUs, so they typically sit there idle. And the most common place where this manifests itself is relational database systems, where your DBAs are sitting there waiting for queries to return. The RAM's not fully utilized, the CPU's not fully utilized, and that's because you're sitting there waiting on disk I/O. So a simple solution is I/O memory. Basically, Fusion I/O took a step back, and they looked at how would we architect the new storage solution if we use NAND flash as the centerpiece. So those of you that aren't familiar, NAND flash is the same memory chips that are available in your USB thumb drives, they're in your smartphone, and it's non-volatile. And when I say non-volatile, that means you can remove power from it, and the data still is maintained on the card. So we take these and we put them on an array and put them on the PCIe bus. Now this is a major distinction. Most solid-state disk manufacturers actually put them behind disk controllers and disk protocols, and they put them in a drive slot. But by doing that, you're effectively crippling the NAND flash in terms of its performance. By putting it behind this disk controller, it can only get so much bandwidth and it can only drive so much I/O because it's trying to talk disk protocols. We believe that memory belongs on a bus, which is why we've designed this device to run on the PCIe bus. And by doing that, we get very low latency. So this kind of illustrates the point. So what you have is I/O memory in the server, right next to the CPU, very low latency, as compared to if you were to put an SSD or solid state out in the SAN, you'd have to travel out through the network and back, and it would generate milliseconds of latency. But because we're NAND flash, we're on the PCIe bus, which is the most direct route to the CPU, we can get microsecond latency, orders of magnitude difference. So when you think about Fusion I/O, think of capacities and persistence and economy of a disk, but closer to the performance of DRAM.